Let's imagine we have a semicircle of unknown radius or diameter. Say we have two congruent inscribed semicircles, each with an area of 4 square units. If we could draw this line segment from corner to corner, such that the line segment is also tangent to this semicircle, what is the area of the large semicircle? Let me show you how it's done. First, let's locate the centers of the semicircles and draw the radius of each. Each semicircle has an area of 4 square units, which tells us they have the same radius length. Assume that radius is r. The formula for the area of a semicircle is 1/2 times pi times radius squared. Substitute a equals 4 into the equation. Multiply both sides by 2 to remove the denominator, and then divide both sides by pi. The radius squared is 8/pi. We will get back to this equation for later. According to the inscribed right triangle theorem, when one side of an inscribed triangle is also the diameter of the circle, then the triangle is a right triangle, where the angle opposite of the diameter is the right angle. Applying this theorem to our problem, we know we have a right triangle, and this is the right angle. Once again, locate the center of the semicircle. From this center, draw the radius to the tangent line as shown. Recall that the radius is always perpendicular to the tangent, so this is a right angle. Now we can notice that we have two corresponding right angles. Using the converse of corresponding angles theorem, we now know that these line segments are parallel to each other. By virtue of the corresponding angles theorem, these two angles are congruent. Therefore, this triangle and this triangle are similar triangles by the angle-angle, or similarity theorem, because they have two pairs of congruent angles. Recall that the radius of these small semicircles is r, so this is r, and this is 2r. Let this distance be a, and this distance be b. Similar triangles have proportional corresponding sides, so the ratio r over a is equal to the ratio 2r over a plus b. Let's write it down and solve. Next, cancel out the radius r, and then cross-multiply. We now get a plus b is equal to 2a. Transpose a to the right side. Equation becomes b equals 2a minus a. That's right. b is equal to a. This means that the center of the small upright semicircle is also the center of the large semicircle. This information is necessary to prove that this distance is actually the radius of the large semicircle. The next step: connect the centers of the two smaller semicircles by a line segment. This segment has a length of r plus r, or 2r. These two lines are parallel, so by corresponding angles theorem, this angle is also 90 degrees. Now it's time to apply the Pythagorean theorem on the right triangle. The hypotenuse a squared is equal to r squared plus 2r all squared. 2r all squared is 4r squared, and the sum of r squared and 4r squared is 5r squared. The area of a semicircle is 1/2 pi times radius squared. Note that the radius of the large semicircle is a. Substitute a squared equals 5r squared into the equation. From earlier calculations, we have obtained r squared equals 8/pi. Simplify the expression and you get the area, which is 20 square units,